So problem set for chapter 7. So which of these involve a chemical reaction? So ice melting upon warming, that's a physical change, so no. Electric current passing through water resulting in the formation of hydrogen oxygen gas that appears bubbles rise in the water. Yes, that is electrolysis, as a matter of fact. That is a chemical reaction. You're creating new substances. You're cracking water into two different things. Iron rusting, this is also a chemical reaction. You're forming iron oxide. Bubbles forming when a soda can is opened. That is not a chemical reaction at all. That's just the carbon dioxide just leaving that's dissolved. I guess you could argue it because it can form carbonic acid. So that one is a little ambiguous, but based off of the stuff in this chapter and the level that you know things, it's really just it's not. So, but you could argue that it's a chemical reaction, but that's kind of beyond this course. So how do we write chemical reactions or balance chemical reactions? And for chemical reactions, it's important to have the same number of atoms on each side of the equation. So when you do this, you pick an atom and try to balance it on both sides of the equation. So for this one, you can pick the silicon. Silicon's already balanced, and balance oxygen next. And so so to balance the oxygen, you're going to have to put, there's two oxygen atoms there, and you're going to have two there to have on two in front of the carbon monoxide to have it be two oxygens in there. So now we have, now the next thing we do is balance the carbon. So we balance the silicon, balance the carbon, and if you look at this, there's one carbon on the left, and there's three carbons on the right, so you have to have three before the carbon there, and on the reactant side to have it be balanced. And now go and double check everything, make sure all of the atoms are accounted for, and yes, they're all accounted for, so this is a balanced chemical reaction. So the procedure is more or less pick an atom, balance it, and then balance the other ones, and then keep on going. It's okay to do fractions as you go through this. At the end, there can be no fractions, though, so it depends on how you want to do it. So here we're going to do another balanced chemical reaction, and this one, you're going to have a fraction because the hydrogen is an odd number here. So the combustion of octane. And so if you look at this, pick one. I'd probably pick carbon as a good one to start off with. So there's 8 carbon atoms on the left, and then you have to put 8 in front of the carbon dioxide on the right. So now balance the hydrogen. So there's 18 hydrogens on the left. So you need to have 18 on the right. So how do you do that? You multiply the water by 9. So looking at the the total number of oxygen atoms, there's 25 on the right, and then there's 2, so you need 25 halves before the oxygen. And of course, that you can't have a half, so we have to multiply the entire equation by 2, and we get 2 octanes plus 25 oxygens make 16 carbon dioxides and 18 waters. So now that is totally balanced. So notice that each one of these is balanced. All the atoms are balanced on each side. So let's balance this equation here. Aluminum reacting with sulfuric acid to make aluminum sulfate and hydrogen. So when you balance this, one of the things that you can note is that you can look at it in terms of units of sulfate. So you can balance each of the ions, but the fact that the sulfate ions are on both sides of the equation, it might be easier to just think of the SO4 as a unit, because it's not that unit is not breaking up. And if you look at the aluminum sulfate there's 2 aluminums and 3 sulfates, so you can right ahead put 2 in front of the aluminum and 3 in front of the sulfuric acid to keep those balanced. And now then the last thing is just to look at the hydrogen. And so there's 6 hydrogens on the left, so you need 6 hydrogens on the right. So you put a 3 in front of the hydrogen gas, and now it's balanced. So this one actually has a shortcut. If you wanted to, you could of course go through and balance each of the atoms, but due to the fact that the sulfate, the SO4 group, stays together, you can really just make that a shortcut when you do this. And of course, when you're doing things like this, the easier you can make it on yourself, the better. So and let's look at this one. Iron plus hydrochloric acid making iron 3 chloride and hydrogen gas. So there needs to be, start off with the irons are easy, already 1-to-1. Now let's do the chlorines next. There's 3 chlorines on the product side, so we need to put a 3 in front of the HCl. And now we have 3 hydrogens and 2 hydrogens, so we're going to have 3/2 hydrogen gas, and that's a fraction, so we have to multiply the whole thing by 2, and then we get the following equation there: 2 irons plus 6 hydrochloric acids makes 2 iron 3 chlorides and 3 hydrogen gases. So yes, these are all whole numbers, and so now we're good. And here's the check. So we have to figure out that the compound is soluble. To look at the chart there, and you look at bromides. So halides tend to be soluble with a couple exceptions, and silver is one of those exceptions. So for A, silver bromide is insoluble. Calcium chloride, chlorides tend to be soluble. Calcium is not an exception, so calcium chloride is soluble. Lead nitrate, all nitrates are soluble, so lead nitrate is soluble. Lead sulfate, sulfates tend to be soluble, but lead plus 2 is an exception. Therefore, it is insoluble. So that's the way you follow through that. And I don't have the chart up here, but if you look at the chart and go through and check that, and it's a logic argument. So how do you write equations for precipitation reactions? So you got to figure out what is precipitating first. So we have sodium carbonate here reacting with copper chloride. So I have to look to see what's going to be soluble and insoluble. So it's going to be the double exchange reaction. And so to see, is sodium chloride soluble or is copper carbonate soluble? And sodium chloride is soluble, so that one's not going to form a reaction. Copper carbonate, though, that is insoluble, so that will fall down. And carbonates are usually insoluble in general, and copper is not an exception to the rule. And so we have a reaction here. And then, so just write out the equation. Sodium carbonate plus copper chloride makes copper carbonate and sodium chloride. Now we balance them. So let's see here. We have 2 sodiums on the left, and we have to put a 2 in front of the sodium chloride on the right. So carbonate, 1 carbonate on the left, 1 carbonate on the right, 1 copper on the left, 1 copper on the right, and 2 chlorines on the left. And now we have 2 chlorines with the sodium chloride. So putting the 2 in front of the sodium chloride does make it balanced. So checking all the atoms that way. And let's look at another one here. Lithium nitrate plus sodium sulfate. So you have to look to see, is lithium sulfate soluble or insoluble, and is sodium nitrate soluble or insoluble? And all alkali salts are soluble. So actually this reaction here, if you look at this and look at the combinations, these are all soluble. So this is no reaction. So when you do this, you write no reaction. You can also write RXN, like no reaction, and you can write reaction as RXN. That's also common for stuff like this. So we're still going for some of these precipitation reactions. So lead acetate plus sodium sulfate. So sodium, you probably already guessed, sodium salts are all soluble. So the question is lead sulfate insoluble? And sulfates tend to be soluble with the exception, and lead is one of the exceptions. So lead sulfate is actually insoluble. And now let's write the reaction here. So if you write out the equation, start off, and this is the molecular equation, by the way. So lead acetate aqueous plus sodium sulfate aqueous reacts to form lead 2 sulfate, I should say, lead 2 sulfate solid and sodium acetate. Well, then let's count the number of each of the groups. There's 2 acetates on the left and then only 1 on the right, so put a 2 in front of the sodium acetate to balance that. 2 sodiums on the left and the sodium sulfate, and then adding the 2 now balances the sodium. So actually now that's balanced. So the equation as written there with the lead acetate plus sodium sulfate making lead 2 sulfate and 2 sodium acetates, that's balanced. So there you have it. So let's talk about complete ionic and net ionic equations. So looking at this reaction here, lead nitrate, lead 2 nitrate aqueous plus 2 lithium chloride aqueous forms lead chloride solid plus 2 lithium nitrates aqueous. So that's the molecular equation. And now let's write the complete ionic equation. So we're going to split lead nitrate up into lead plus 2 aqueous plus 2 nitrates aqueous, and lithium chloride to 2 lithium aqueous and 2 chlorides aqueous react to form lead 2 chloride solid plus 2 lithium ions aqueous plus 2 nitrate aqueous. So now when we look at the complete ionic equation, we have spectator ions. The lithium and the nitrates are spectator ions. So you can, when we write the net ionic equation, remove those. And now we just have the lead plus 2 chlorides making lead chloride. So these are the ones that participate in the reaction. So then the net ionic equation removes any spectator ions, in this case the lithium and the nitrate. So write a molecular net ionic equation for between the nitric acid and calcium hydroxide. So first of all, write the equation: nitric acid plus calcium hydroxide forms water and calcium nitrate. We got to balance it. So 1 nitrate on the left, and so we need to have, and we have 2 on the right, so we need to put a 2 in front of it. And also the calcium, so it's 1 to 1 for that, that's fine. And then the hydrogen is going to add then to the OH to form the water, so we have to have 2 waters there. So balance the equation, and then for the net ionic equation, it's really just, if you look at everything, the nitrate, it's a strong acid, HNO3 breaks apart completely. It's really sort of like H plus or H3O plus aqueous and nitrate aqueous for HNO2. And the calcium is aqueous. So those are the spectator ions. So the nitrate and the calcium can go away, and you just get H plus, 2H plus 2O minus, 2H minus form 2 waters, or you can divide by 2. So that's really what acids and bases do when they react. You form water and salts, at least in aqueous reactions. So it's pretty predictable. You see a pattern, right? So let's write equations for gas evolution reactions. So nitric acid plus sodium carbonate. What's going to react? And the carbonic acid can decompose into, it's going to form carbonic acid. Carbonic acid composes into water and carbon dioxide. So look at this equation, then the nitric acid reacts with sodium carbonate, forms water and carbon dioxide and sodium nitrate. But we also need to balance it. So there's, if you look at the sodium, there's 2 sodiums on the left, and there's only 1 on the right, so you're going to put a 2 in front of the sodium nitrate. And now we have 2 nitrates, so we need to add 2 in front of the nitric acid. And then there's 1 carbon, and then the oxygens. The 2 hydrogens from the nitric acid react with that 1 extra oxygen on the carbonate. So then all of these then are balanced. So that is balanced. Which of the following are redox reactions? So you have to have a working knowledge of the oxidation states. So for A, magnesium metal there, it's a free element, has oxidation state of 0, and then reacts with oxygen to form magnesium oxide. The magnesium oxide, alkaline earths tend to be +2 in compounds. So magnesium goes from 0 to +2. It is being oxidized. Oxygen is going from 0 to -2. It is being reduced. Therefore, that is a redox reaction. So for B, this is 2 hydrogen bromides react with calcium hydroxide to form 2 waters and calcium bromide. If you look at all of the oxidation states, they are all the same. Hydrogen is +1, bromine is -1, calcium is +2, oxygen and the hydroxide is -2, hydrogen is +1. Same as in the water, and the calcium is still +2 and bromine is -1. So this is an acid-base reaction. There's no oxidation reduction in there. For C, calcium metal reacting with chlorine gas to form calcium chloride. Both are elements in the reactant side. The oxidation state's a 0 on the right. Calcium is +2, chlorine is -1. There are transfers of electrons, so this is in fact an oxidation reduction reaction. So C is 1. Now for zinc, so we're on the D. Zinc metal reacting with iron +2 in solution forms zinc +2 in solution and iron metal. So in this case, zinc is giving 2 electrons to iron. Zinc is being oxidized, iron is being reduced. So D is in fact an oxidation reduction reaction. So let's talk about writing combustion reactions. And methanol reacting with oxygen to form carbon dioxide and water. So we need to balance this. And starting off, the carbons look initially balanced. There's a 1-to-1 molar ratio for that. That's fine. But now let's look at the hydrogens. So there's 4 hydrogens on the left and 2 on the right. So we've got to add a 2 there in front of the water. So now then we have to count up all the oxygen atoms. So we have let's see here. We have 4 on the 4 oxygens on the right and 3 on the left. So we have to double it, and doubling things in order then to balance out all the oxygens. You're going to have a 3 there. So you can see that there's an odd number, and it's keeping true the 1-to-1 ratio of the methanol to the carbon dioxide. So after you double everything, you can count again, and starting not including the oxygen. So not including the oxygen, we have 2 oxygens, like not including, I'm saying the O2 oxygen, not including the diatomic oxygen. You have for the 2 methanols, you have 2 oxygens, and on the right you have, for CO2, you're going to have 4, and then another 4, so there's 8. So you have 8 oxygens on the right, and then you need to place 6 more oxygens. And so how do you place the 6 more oxygens? You put a 3 in front of the O2. So that's the logic behind that and the thinking process. Hopefully, this me speaking it out is helping you follow how to balance that one. That one's a little more difficult. So classifying reactions, what they do. So sodium oxide plus water to make sodium hydroxide. That's a synthesis. You're making something from other more complex thing from other things. So the barium nitrate plus potassium sulfate, making barium sulfate and potassium nitrate. You can call it a precipitation reaction, but the type of reaction is double replacement. So you're replacing 2 things are replacing each other. An aluminum reacting with rust to form aluminum oxide sapphire and liquid iron. This is known as a thermite reaction, and it's an oxidation reduction reaction. Then for hydrogen peroxide, that's a decomposition. That's forming other things, and also calcium plus chloride, making calcium chloride. That's a, you could argue that's a synthesis. It could also be oxidation reduction. What do you say? Yeah. Okay. Well, it could be either. That's also, it's because you can, it's a synthesis reaction, but it's also an oxidation reduction reaction. So it depends on both actually work for that one. So which are chemical reactions? Copper turns green, exposure to the air. That's a chemical reaction. You're making a new reaction from that, from the color change. When you form a gas from mixing sodium bicarbonate and hydrochloric acid, yeah, the gas is an evidence of a chemical reaction. Liquid water freezes to form solid ice. That's a physical process. There's no exchange of atoms. Pure copper penny forms bubbles. A dark brown gas when dropped in nitric acid, and nitric acid turns blue. Oh yeah, so because of the gas and also the color change, then that is in fact a chemical reaction. And thank you for listening.